That's the answer. It was right in front of me. I didn't need to do much once I recognized it. What you're not going to do is go from here to here. No logic, because you don't have a chain rule factor sitting there. That's trying to do too many things. When I say eliminating steps, people sometimes confuse that. Doing a step in your head is still doing a step. I'm talking about literally eliminating steps that are not necessary. If you can do a problem in 1 or 2 steps, write them out. Never do math in your head. I don't care if you can. I can do math in my head. When we're doing things involving calculations, if you've been in my class, you already know this. We're doing things involving calculations. I'm waiting on you guys to calculate it. My brain works differently. My brain already computed the answer before we were even done with the problem. I don't think about it. It's just the way my brain works. I've already done the calculation. I'm just waiting for you guys to hit it in your calculators. Do the calculation. When you don't show your steps, when you do steps in your head, here's a problem. Most of you are going to take linear algebra in the next year. Oh, probably the most cool subject on planet Earth. You're going to do matrix algebra and all sorts of things. And some of the problems can be really long. And a lot of students will try to go too fast and they'll skip steps. The reason you never want to skip steps, because at the end of the problem, if your answer is not correct, it is impossible to identify where the error occurred. Which means 100% of the time, every time you're not perfect, guess what you have to do? The entire problem from the beginning. In every single situation in math and science, you're always doing, by the way, so my speed of doing everything in my head in the long run costs me an unbelievable amount of time, because anything short of perfection means every problem has to be done in its entirety. But if a problem is long and you're writing things down, it didn't work, oh, I found my error, what do I have to redo? Just from that point on. That's for you. Now, you guys are going to get jobs, real jobs. Cool jobs that pay a lot of money and drive nice cars. You're probably going to be working with teams, or certainly you're probably not owning the company on day one, which means all work that you do is meant for someone else's eyes, and it will not be looked on highly if you just have results without any explanation of where your results came from or any justification. So you always want to show everything so the person reading it can follow what your thought process was. Has anyone here ever written computer code? Like big computer programs? Do you use comments? When I taught programming during the 90s here, and I would plead with the students, you're writing maybe 100 lines is not a long program in real life, but in a programming class it might seem long. And comments was when you write words within brackets saying this portion of the program is designed to do this. This is designed to do this. Do you know why you do that? Because in real life, I know professional programmers, they say because they're often asked to go back and tweak it, have it do more things, do other things. Because they left themselves the comments, a trail of breadcrumbs, then they could take that portion of the program and change it, make it better, do whatever, because they left a simple, clear explanation. 100% of the time, if there's no comments, they have to start from scratch and write a program. And that's really time consuming because they have no idea. You have thousands of lines of code. I don't care how good you are, you're not going to read every line of code to try to figure out the point of the program. That wouldn't really be very efficient. So in a math sense, always explain what you're doing so that when you go back and look at it, you can make heads or tails. You may not do another integration parts problem until the first exam. I don't care if you're perfect today. Does that mean you're going to be perfect at it in a month? If you don't do any in between? Yeah. So one of the reasons I'm not saying err on the side of too much. No, say everything that needs to be said to justify the steps so that when you go back and look at it later. The silliest question I get asked in every course, and you got a perfect score on that first quiz, and then when you're reviewing it for the exam in a month, you come to me and say, Mr. Brown, I have a perfect score here, but I didn't write that much. What was I thinking on this problem in order to get this answer? Those are the words people usually use. And I'll say, you were thinking that the Celtics probably should have whooped the Lakers the other night when LeBron and AD weren't playing. Like, I don't know what you were thinking. People actually ask me that question. What was I thinking when I wrote this? Seriously? When's the next season of Stranger Things coming out? I don't know what you're thinking. If you don't leave a trail of breadcrumbs, you literally have to start everything from scratch again. And that's totally inefficient, and that is not lazy. That is so not lazy. Now let's do this problem the longer route. And here's why it's the longer route, because that may be the route you're more comfortable with. You're looking at that and going, oh yeah, tangent, duh, that's my u. I see a secant squared right there. You see something else, you are not wrong. You're absolutely correct. If a problem can be done more than one way, which way should you do it? The answer is yes. Whatever way you see first. If I ask this question on a test, I am not going to get one unique solution. I'm going to get more than one because there's more than one path. So in the second case, I want to let u be the tangent function, and then I want my du therefore to be secant squared x dx. Now, what do I have to do first? I have to rewrite it as secant squared x. I'll put the tan x, and then I'll put the secant squared last. I always like, it's easier for me if I put my chain rule factor at the end. Have I changed anything from the original question? Have I done anything yet? No, it's exactly the same thing. So what do I want to do now? We did a problem like this earlier with sine cosine. I want to use the Pythagorean identity, which means I actually have to know what the Pythagorean identity is. Secant squared is equal to you only have two choices. Times, no, plus. Agreed? 1 plus tan squared. So now I want to multiply this out. I can't integrate a product here. It won't work. I have to multiply this out. So I've got tan x plus tan cubed x times secant squared x dx, and do use parentheses. If I don't use parentheses, it is quite different. Now, if my u is tangent, there's my du. So what is the form now of my integral? It's now of the form what? U plus u cubed du. Can I integrate that easily enough? Yeah. Let's try it. Let's see if we can do it without changing the variable. We've already stated what the substitution is. There's no ambiguity. What's the antiderivative of u?
1/2 tan squared.
Well, let's say in terms of u. It's 1/2
u
squared. And that was my u. What's the antiderivative of u cubed?
1/4
1/4 u to the 4th plus c. Which answer is better?
the first one.
Well, which answer was probably, I don't want to say easier, it was probably maybe one step less. Probably the first one. Which answer would you rather use, though?
Tan.
What are you more comfortable using, tangent or secant, probably?
Tan.
Probably tangent. So they're both good. Now, how do I decide which one I would actually want to use before I start the problem? Now, you've heard me say it before. I will probably say it again at least another 3,000 times. It's not about right or wrong. So what's the most useful form? And I can't tell you that. You're in a physics situation. You're in a higher level math situation. You are using the answer for the next step. But later on, look ahead and say, are we using tangents in this problem? Are we using secants in this problem? Heck, we might only be using sines and cosines later on. The better answer is the answer that will translate best later when you're doing other things. And I cannot tell you what that is because I don't know what it is. It depends on the situation. They're both perfectly valid. Which one you choose to do has more to do with how am I going to use this in the future. Does that make sense? If I wanted to check through differentiation, that's an interesting thing. Because if I take the derivative of either one of these, am I going to get the original problem back again? Only the derivative of this one is going to give me this back at the next step. Because what's the derivative of this one going to give me? Well, it's going to give me this. And I'd have to multiply it back out to get this, and then I'd have to put the secant. Do you see that? Oh. So if I wanted to check the differentiation, right? 4 secant cubed times derivative of secant. But in terms of usefulness, it doesn't matter. I think most of you would opt, if you had the choice, to do the first one just because it seemed more direct, but they're both correct, and you're definitely not wrong. So you're checking your answer in the back of the book. You might see one, you might see the other. The problem is it's really hard to navigate back and forth, isn't it? I mean, I have to do a lot of changing. I would have to change secant squared to 1 plus tan squared and then square that and then expand that and all that, but I would eventually get that. And so on. Okay, question? Okay? The problem that we did last day, we did secant cubed. The technique we're doing right now is just simply straight up U substitution, integrate. We couldn't do that on the secant cube. That required an integration by parts. That's why I did that one last day. But what you'll often see is in the homework, in the Swakowski book, this is section 9.2, whereas integration by parts is 9.1. In most calculus books, the very next section is just sort of the random trig integrals. This is not technique. You're using a U sub, or you're using Pythagorean identities to make it, easier to interpret, but you're not using anything clever. The reason you're doing this is because this stuff's going to come up a lot in the next section that we're doing, which is the first half of Monday's lecture. Okay? Now, what if you have something that looks totally whack? Okay, I like totally whack. Totally whack is cool. All right, I have something, let's say, let's do something really crazy. I want to do, how about something like this? Yeah, this is pretty cool. Does this look like any antiderivative formula you're familiar with? No, there's no formula that looks like this. On day one of calculus, we haven't done derivatives and integrals yet, but I like to show people how to navigate through certain trig identities just using what you already know in order to make certain things easier to approach. Products are always superior to quotients in mathematics. Sums are always superior to products. In other words, think of the ease of working with a sum versus a product. Think if you had to graph something or you had to solve something. So we often manipulate things. So I'll give you a simple example of one I like to do I do this on day one of Calc 1, because it's going to come to this one, and that is employing certain things. Okay? So there's an identity on the cover of every calculus book. There's a bunch of identities that look like things like this. Let's say it might be sine x over 1 plus cos x. That might be, and it'll give you versions of this. If I have to differentiate this, yuck. If I have to integrate this, yuck. If I've got to solve a problem algebraic with, it's a quotient. I really, really don't like trig functions in the denominator. But if you think of the Pythagorean identities, every one of them, right, a sum of squares equals something else. Let's do sine squared and cos squared. I usually like writing cos squared. But if I solve for either one of these, let's say I'm solving for sine squared, and this is true for all three Pythagorean identities. Can't all three Pythagorean identities, if you move one term, be written as a difference of squares? All three of them can be. Tan squared plus 1 equals secant squared, but secant squared minus 1 equals tan squared. Secant squared minus tan squared equals 1. Right? 1 minus cos squared equals sine squared. 1 minus sine squared equals cos squared. Why is that important to know that every one of them can be written as a difference of squares? Because that means every one of them, therefore, can be factored into the product of, what's the word? Starts with a C, ends with conjugates. Any guesses? Conjugates, good. Way to go for me. If I have a difference of squares, it can be factored into conjugates. And you've all done algebra like this where you use the conjugate of something to make it easier. When you're working with square roots, often it's easier. But if I know this, this again, this is day one. This is the first 45 minutes of I do this in Calc 1. Oops, sorry, that's it. X. Is this a legal move? Yeah, multiplying by 1. Now, don't distribute the top. But I do want to distribute on the bottom. This is the sort of, by the way, in a trig class, this is the stuff that is the most valuable for you to leave with. The manipulation of the trig terms, using their definitions, using Pythagorean identities, things like that, to take a complicated thing and write it easier. In trig class, it was always verify the identity. Remember that? So you manipulated it to try to get it to something smaller. We do this all the time in a math situation. What's my denominator now?
1 minus cos squared.
Is that meaningful? Yeah. Because now that's what?
Sine. And then the sign on the bottom.
Can I do that?
Yeah.
Absolutely. So now, I took one nasty quotient, and I just wrote it as another nasty quotient. Oh, great. That was a huge improvement.
Yes, it is.
Years ago, I had students tell me that, I said, what do we do? And they'd say, do the heart technique. And it took me the longest time to figure out what they're talking about. And I realized when you're breaking it up, it kind of looks like a heart. This is the most common thing that I've ever done in my entire life in a math setting. And I do this probably every day in every calculus class I teach. And when I pull them apart, what do I get? 1 over sine minus cos over sine. And now I'm done. I just took something that was completely useless in a calculus sense. To do the calculus on this would be a nightmare. And this is identically equal to that, which is not a quotient. It's not a product. Can I differentiate that easily? Yeah, I've got to have my formulas, but can I do that? Yes. Can I integrate both of those easily? Yes. I want you to do the integral of this. You can't do the integral of this. You have to change this into something you can integrate. So what do you think the first thing we should probably do is? Same thing we did over there.
Multiply top and bottom by the conjugate.
By the conjugate. Now, I don't know if that's going to fix it, but I do know in the end I can probably make it not a quotient anymore. Where this would be a problem, tell me where this would be a problem. If that's not a 1. If it's anything other than a 1, there's no Pythagorean identities. Well, that'll never come up, will it? No, that won't come up until, that would never come up in your math careers. It won't come up until, hold on, 2 weeks from today. And it's the most horrible technique you'll ever learn, and it's the only one that exists for doing things where that's not a 1. I affectionately refer to it, all the students who have been in my higher classes, we affectionately refer to it as the evil trig. For lack of a better name, you're going to learn the evil trig. That's the trig that is so nasty, there is no math you've ever learned in your life that will address it. But what if that was a 2? Yeah, what do we do? So, CC's absolutely correct. We want to do this, and then we will play with this until we have something useful. Okay? So what do I have on top? Well, 1 plus sine. What do I have on the bottom? 1 minus sine squared, which is the same as
Cosine squared.
cosine squared. Can I now pull these apart?
Yeah.
In fact, not only can I pull these apart, I just made this up, but I don't think I could have made up a happier problem. What's 1 over cos squared?
Secant squared
Secant squared.
plus
1 over cos times sine over cos?
secant tan.
Secant tan. And what are we doing with this? We're integrating it. Oh my gosh, if that is not cool, I do not know what is cool. Okay, I may not know what is cool anyway. If you ask my kids, I don't know what's cool. This algebraically is identical to this one. The first one's impossible. There is no technique you'll ever learn in your life that will address the first one. There's no chain rule factor, there's no substitution, there's nothing. But we used Pythagorean identities and definitions. Where do we use definitions? That 1 over cos squared is secant squared. That's definition. Okay? That 1 minus sine squared is cos squared. That's Pythagorean identity. So we used identities, definitions, to rewrite the integrand into this. Can I now attack this? Yeah. Are these ones we should know at this point? Yes. And if you don't know them, you have a sheet of integrals in front of you to review them until you are familiar again. What's this guy? Tan? Wow. That's cool. Can I check this through differentiation? I can, well, if I differentiate this, what am I going to get? I'm going to get this. I'm not going to get this. I had to apply identities and definitions, didn't I? So to go backwards from here to here would be a little bit of work, wouldn't it? Does everybody understand that? So you used identities and definitions to change the problem into one you could do. So the only check is going to take you back one step, just so you know. When you differentiate that, you're not going to get 1 over 1 minus sign. But you will get the previous step. But this is, again, this is using the trig that you knew before you took calculus. And unfortunately, again, I'm not going to criticize because I haven't taught a course, other than statistics, I haven't taught a course full of calculus in a very long time. But I think there's a lot of time spent in trig that is not really critical information. We spend a lot of time on minutia, where the manipulation of the trig functions and the verify the identities, I think, were one of the more important things. You can seamlessly go back and forth between expressions to say, well, this one is identically equal to this one is not useful, but this one is. See, that first quotient is what I'm asking you, but it's not useful. I can't use it, but I changed it into something I can using only baby trig. This is not complicated trig. There's no double angles here, right? I'm not being clever in any way. But if I can't do all of this, then I'm kind of dead in the water there, aren't I? You really don't like quotients involving trig in general. It's just harder to work with, okay? You guys with me so far? It's like, wow, this is some gnarly stuff. Well, it might be. Now let's do one more. I want to do one thing because there's a tendency that we often overkill things when we're doing calculus. We substitute when it's not necessary. My favorite one, Calc 1, is, I ask a trig integral, or I ask an integral in general. Let's just say I'm doing something like this. Okay, this one's pretty easy, right? I'm gonna let u be x squared. You all agree with that? But I'll ask this question, and I'll say, and I'll get this. Let u equal x, then du is dx. And so now this is sine u du. Have I said anything incorrect? No. Have I said anything of value?
No.
No, I just rewrote exactly the same problem verbatim. I just decided to write it with a different letter of the alphabet. That is not a substitution. And as funny as this is, I had some people turning the first quiz, and they did this on some of the problems. I'm not going to embarrass you, but let u equal x, and then they rewrote the problem with u's rather than x's, because I guess they're more comfortable with u's. That's not a substitution. There's not even a place for a substitution. I could have used a q or a t or an h, right? It doesn't matter. No, that's a substitution. Now, there is a problem that I did earlier, or actually did a couple problems earlier, where we integrated the cosine, not of x, but of a constant times x. And some of you were not comfortable with that. You're like, don't you have to do a substitution? A lot of the substitutions we do are actually not necessary. So I'm going to ask you a simple question. All right, let's keep it really easy. I want to do the cosine of 3x minus e to the 4x plus the secant squared of 2x. Now, can I let u be one thing? First of all, this, by the way, this is in every calculus book, this question. And I will fill up the entire board doing the formal calculus book way. Very first thing I have to do is break this up into 3 integrals. It's not possible to do this at one time with the same substitution because I have 3 different arguments. Do you agree? So I break this up into 3 integrals, and then the first integral, my substitution will be 3x. My second integral, the substitution will be 4x, and the next one, the substitution will be 2x, and then I will get my chain rule factors, and then we'll do a substitution, and yada, 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 yada. I show this in Calc 1, and I maintain you absolutely have to give me the answer to this as the next thing you write. There is no step in between. The next thing you write should be the final answer. There is no substitution necessary. But wait a minute, my arguments aren't x. No, they're not, but they're scalar multiples. So I'm going to show you something really simple. And if you didn't learn this in your calculus class, I feel like you were kind of cheated. K is any constant. I know the derivative of f of x is f prime of x. No big deal. What's the derivative of f of kx? Well, it's f prime of kx times k. K would be my chain rule factor. So if I asked you to differentiate the sine of 5x, aren't you going to say cosine 5x times 5? Am I right? Right, you're just going to multiply by the scalar. There's no function going on, just a scalar multiple. So therefore, if I want to integrate, I want to integrate f prime of kx dx. Well, let's do a formal substitution. Let u be kx, because let's assume k is not 1. That'd be boring. Then what's my du? It's k dx. So I cannot do this unless I have that k, and I'll put 1 over k. Now it's f prime of u du, which means it's f of u plus c, or There, I did it. I integrated f prime of kx, and what's my answer? F of kx times 1 over k. Absolutely, I want you to do this. Never do a substitution if your argument is a scalar multiple of x. You never have to. There is no problem that exists where you have to. Okay, let's do this. What's the antiderivative of the cosine function? It's the sine function. What's the antiderivative of exponential? It's exponential. What's the antiderivative of secant squared?
Tan.
Tan.
1/3. 1/4. Half.
If you did more work than this, you wasted your time and probably didn't even get the right answer after all that. How many have seen what I just did in a Calc 1 class? Well, if you're in my class, of course you did. How many have seen that you never have to do a substitution? In fact, you shouldn't. It just makes it more confusing. Yeah, it's a waste of time. But I might get the wrong answer because I did things that were unnecessary. If one of these was x to a power, no, I got to do a substitution in that case. But they're all scalar multiples of x. So earlier when I was integrating the cosine of 2x, I know some of you were uncomfortable that I just flat out integrated it without doing any work, but I'm just using this. As long as it's a scalar multiple of x, the scalar shows up as a coefficient. When you differentiate, the scalar's being multiplied. When you integrate it, it's the reciprocal of the scalars being multiplied. That's absolutely across the board. In fact, we just did it here, right? Shows up here, shows up here in the integral. Absolutely, always. So, therefore, it really shouldn't be something that troubles us in general. Okay? Any questions? Okay, go ahead and stop that. Colorado,